Good afternoon. Welcome to the University of Connecticut and to the Pfizer Colloquium of 1979. I'm Ellis Page. Because I am a devoted user of statistics and a friend of the statistics department, I've been given the honor of convening this very special colloquium. Today is a rare day when we come in contact with the history of statistics, this remarkable 20th century achievement of the human intellect, through the presence and voice of one of the pioneers and architects of that achievement, Jerzy Neyman. As a user and appreciator of this achievement, we welcome Dr. Neyman on behalf of the University of Connecticut and those statisticians and friends assembled here and those who will later see this recorded performance. Our special thanks to the Pfizer Corporation for providing the funds and encouragement to make it possible, and to the Statistics Department for so enriching our intellectual experience. Now to the Master of Ceremonies of this event and the organizer most responsible for bringing it together, Dr. Harry Poston of the Statistics Department.
Thank you, Professor Page, for your welcoming remarks. My job today is to introduce the speaker. However, before I begin, I'd also like to take this opportunity to express my appreciation to the Pfizer Corporation for their financial support of these colloquia. It is through their encouragement and support that we are able to bring to the University of Connecticut the most distinguished statisticians in the world. Today we are fortunate to have as our speaker for the second annual Pfizer Colloquium one of the world's most distinguished statisticians. His research career has been long and productive, and he has made many important contributions to our field. In fact, it has been said of some of his early works that they represent directions of thought which have dominated theoretical statistics for several decades. Because of the significance of his contributions, we are filming this colloquium for archival purposes. The filming is under the sponsorship of the American Statistical Association and is the first in a series of recordings of distinguished statisticians for their film archives. At the request of our speaker, the format of our colloquium will be similar to past meetings of the Royal Statistical Society, in which, following the presentation, several invited respondents provide comments on the speaker's topic based on a reading of the paper beforehand. We have 3 respondents today, and I will introduce each at the end of the presentation. It is now my privilege to introduce to you Dr. Jerzy Neyman of the University of California at Berkeley. Professor Neyman received his PhD degree from the University of Warsaw in 1923 and subsequently has received honorary doctorate degrees from 5 universities throughout the world. He has been a scholar for more than half a century, and his accomplishments include over 200 published papers, plus authorship or editorship of some 20 books and monographs. He originated and was editor of the prestigious Berkeley Symposia on Mathematical Statistics and Probability, which now consists of 22 volumes. The range of his research is astonishing, or, to put it in his own words, the subjects on which I have worked with some persistence and abandon represents a conglomeration verging on the bizarre. To some degree, I believe this is simply a matter of being a statistician with the opportunity to work in so many fascinating areas. Nevertheless, the range is unusual, to say the least. It includes, on the theoretical side, contributions to set theory and probability, and of course, the foundation work for which he is most famous, the development in the 1920s and 1930s with E.S. Pearson of the beginnings of the theory of optimal tests of hypotheses, from whence came the now familiar Neyman-Pearson lemma. It was also in the 1930s that Dr. Neyman began his development of the theory of confidence interval estimation, which provided one of the basic categories of statistical tools, now used universally by almost anyone who makes use of statistical inference procedures. In the application area, his contributions have also been major. He has made significant statistical contributions to numerous areas: biology, medicine, astronomy, weather modification, health pollution, and accident proneness, to mention just a few. He has received numerous awards for his scientific achievements, including the National Medal of Science from the President of the United States. His research continues unabated today. In fact, the title of a recent publication will indicate that not only has he been an early contributor to the foundations of our profession, but that he is still equally involved in research areas on modern topics. The title of the article, which appeared in Science, is Public Health Hazards from Electricity-Producing Plants. This paper is concerned with an epidemiological study to compare the hazards of both conventional and nuclear plants. Dr. Neyman has for several years been a strong advocate of a comprehensive national statistical health pollution study to involve an extensive sample study of American communities. The purpose of this study would be to assess the effects, if any, of various pollutants, including low-level radiation, on the health of a community. Dr. Neyman's topic today is clustering, reminiscences of some episodes in my research activity. I believe you will find the topic interesting since it discusses a research problem on the clustering of larvae which Dr. Neyman solved in 1939, and from which the concepts and solutions were subsequently found to be applicable to a sequence of entirely different research areas. The variety of applications is extremely interesting, and they have led me to a small subtitle for today's presentation. It is From Insects to Galaxies. I now have the honor of introducing to you Professor Jerzy Neyman.
Well, it's a great pleasure to be here, and I am very grateful for giving me the opportunity of enjoying this meeting. I would like to make the beginning of the modify slightly my presentation prepared by explaining why I enjoyed it. The way I'm going to do it is to quote to you a poem written by Pushkin, or slightly more than a century ago. I read it, I liked it, and for a time I tried to translate it into English. But I was not successful, except that the second wife of Egon S. Pearson helped me with this, and saw that the work is not, if it is appreciated, it's not, yes, my initiative, but without the help of the lady, it would not be completed. So the poem reads this way, the translation. The heart lives with tomorrow and glides through a dreary today. Yet, when today drifts into the past, it will shine with its own magic glow. And this is what gave me the pleasure of writing on this, which began, yes, in the work. The first thing was done in joint with Dr. Beale, whom I lost contact with, but it was done in the, yes, I was still in London in 1930s, late 30s. Then a statistical treatment of the problem appeared in 1939 in one of the journals in Annals of Mathematical Statistics, and then it appeared that the same idea, which was really due to Dr. Beale, is applicable in a series of studies in various domains, all right, you will hear about it. So what was the problem of Dr. Beale? He was an entomologist. He was an entomologist, and he was employed in the Dominion Entomological and Experimental Station, Chatham, Ontario. He came to London, which at that time was really the center of statistical study. Many people from all over the world came there and explained this problem. The problem was of studying the effectiveness of some treatment, some pesticide. Now, all right, he tried to use some standard distributions which came to his mind, hopefully to determine, to be able to test the hypothesis that the treatment, this pesticide treatment, was really effective. And the basic assumption was that after treatment and before treatment, the larvae, which were the subject of study, would be distributed on the field uniformly. And then I asked him, who are the larvae? And he told me that at a particular time during the summer, moths are flying over the experimental field, presumably experimental field uniform as far as is possible. And then these moths lay eggs. Now, eggs are not laid singly, but in what the entomologists called masses. And he showed me this mass of egg, and this was a little stick, somewhat thinner than this cigarette, and it was all covered with eggs, tiny little ones. Now, in due course, these eggs would hatch and produce larvae, to begin with minute, but later on they would grow, and after some weeks they would perform a general census. A general census, and the question would be to estimating, to first of all writing a distribution of these eggs, of these larvae on treated plots and not treated plots, and see whether there is any difference and so forth. These larvae, so the distribution of these larvae over the field will be what? It begins by distribution of the masses of eggs. Then, in due course, many of these larvae would hatch out and would travel for food. Well, of course, larvae probably are food for birds, for other insects, whatever. And so, by the time that the census is performed, many of the original larvae would be dead, would disappear, but some will remain. But they cannot even remain, they cannot travel very fast. And so the number of eggs counted, number of larvae counted in one of the plots, experimental plots, let's have its area unity, would depend on what? On how many egg masses would be around, would be distributed over the field, and then on how these larvae would travel to reach the plot on which you are counted. Now they cannot travel very fast, and therefore the part of the mechanism is the existence of an area of accessibility. Now we cannot travel very fast, consequently, in order that a larva from a given mass could reach a plot, the distance from where it started, from the egg mass to this plot, should not be too big. And so there is a plot, and then this plot is surrounded by some area of accessibility. The shape of this area is difficult to foretell. It is possible that there are on the field directions in which larvae travel faster than in the in the perpendicular direction, particularly if there are rows, and particularly if there are rows of plants, if the plant is something like corn. That was the subject of study of Dr. Beale. All right, so that's the thing appeared to be attractive, interesting, and so we started working. Yes, Dr. Beale contributed a little bit to it, a formula. There is a way of computing these probabilities. Beale produced it, but essentially I think most of it mathematical thing. He is an entomologist, and I was a mathematical statistician, so there is little doubt that I worked on it more and produced. I am more of the author of the paper than he is. All right. Now, a field of applications of this mechanism of clustering was that came to our mind at the time, but two essentially. One is entomology, another was bacteriology, which was suggested by some work of student, Mr. Gossett, or Dr. Gossett, but he published his work under the pseudonym of student. He was employed by a brewery, and the brewery didn't want to suggest to competitors that it would be profitable for them to have on the staff a producing statistician. So that he described now. All right. It did not occur to us, Dr. Beale and me, that the same mechanism of clustering would be applicable, would be operating with some changes in other domains, particularly such faraway domains as astronomy, cosmology, galaxies, and so forth. Obviously, if you look at this clustering, you see the essential points of this mechanism there, but the details must be different. All right, so what are the essential points of mechanism of clustering? First of all, the distribution of cluster centers. So with larvae, there is masses of eggs, cluster centers. Second, there was a dispersal of the cluster members. Oh, I forgot. There is also the size of a cluster, which must vary from one cluster to another. Number of larvae which survive up to the day of the general census, and then dispersal. Well, in connection with this dispersal, slow dispersal, there is also a concept of area of accessibility. So those are the elements of the mechanism of clustering. And to begin with, we didn't think of any other phenomenon which involves this, but then it did occur. Now, let me illustrate, and there will be slides there. The first slide is represents, if I remember right, simply the title page of the paper, that's of 39, contagious distributions applicable in entomology and bacteriology. So that's the thing. All right, and then you can see probably a little bit of what is in the text of this contents and so forth. Then, in order to illustrate that during the writing of the paper we did not transgress the limits, the subsequent several of them tables, slides illustrate where we ended. And so there is one, is just counts of some larvae which are corn borers, and Dr. Beale produced this. Well, there is a comparison. The middle column represents the actual counts in these little squares, and then on the left it is Poisson law, and on the right there is a column of this new distribution which I produced. And if you compare these two columns, you will see that much better coincidence, agreement with the observations. Now, all right, another table refers the same thing, but it refers to bacteriology, and that was inspired by a student. Well, I must say that in these distributions, all right, published in 39, there are many unsolved problems, and these problems, particularly in connection with what is going on now, would be really interesting subjects for thesis. And in fact, this coming summer, we shall have an effort of solving certain problems, and I will be pushing young people to undertake the study of these distributions, particularly the problem of estimating the parameters. The basic distribution here used has only two parameters, which describe really, we depend on these two elements, on these elements of the mechanism, but how to estimate them, it's no optimal way of estimating was deduced, and this would be a very interesting thing to do for a young person, particularly in connection with some further developments. All right, so time went on. California is known as a land of big telescopes. And having lived there since August 12, 1938, it was inevitable for me to become exposed to problems of astronomy, and the people there who were inspiring was Professor Shane, who at the time was director of the Lick Observatory, which belongs to University of California, and also an astronomer who worked there on the Lick, Nick Mayo. And so problems appeared interesting. Yes, there was a contact with problem of clustering, and so we had in the statistical laboratory, Dr. Scott and I, she had a degree in astronomy. She was in the first class that I taught in Berkeley, and then became technical assistant, and then she got a degree, yes, in astronomy, but we had contact with her for a long time. And so something like 20 at least, probably a little more, joint publications frequently with the co-authored by astronomers appeared, and it was quite inspiring. Now, what was the subject of this study? Point is that Shane undertook a study which was, for which I have a great respect, but I couldn't attempt anything similar. He had the telescopes there, and he was studying the motions of stars within our galaxy, within Milky Way. Now, how can you study it? You can study it by observing spectra of these stars, and then the spectrum would indicate the projection of the velocity of the star on the line of sight. All right, but that's just projection on the line of sight. And then there is also of interest the velocity in perpendicular direction. Now this is possible to study in those days by the following method. Someone at year so and so takes a photograph of the sky and gets a plate in which there are those stars visible. Then, at the time it was estimated, 50 years later, someone else probably would take a photograph of the same spot on the sky, photograph, and that would be again the photographic plate, and then they would superimpose the new photograph, the new plate on the earlier plate, and see whether the images of the stars moved. They all move a little bit, and so it was a problem there. But the mere fact is to embark on a research project which would be completed 50 years from now, but you would not be there. Now, that's something which doesn't agree with me. And also it didn't quite agree with Shane. So then every night they would take, he and an assistant, a number of these plates, then these plates would be developed, and then they would have to be stored. Yes, they were stored. But when looking at them, he noticed, Shane, that there are images of galaxies. And the plate, size about, I don't know, a little more than a foot, one way and the other one. This plate, a plate like this would contain, on the average, of course it varies, something of the order of 2,000 images of galaxies. They look different. You see, it's a kind of a fuzzy spot. And so Shane got interested in the distribution of these images of galaxies on the photographic plate. At the time, they already knew, astronomers, that there are some places in the sky where there is a big accumulation of images of galaxies. There was a so-called coma cluster, big cluster. Now this accumulation, of course, was on a photograph. And who knows, it's possible that they appear to be accumulated, these galaxies, but in actual fact, it may be that in our galaxy there are clouds. There are clouds, dark clouds, and they obscure parts of the sky. And so if there is a hole, no galaxy there, on the photographic plate, it may easily mean that there is something which prevents these galaxies from being seen. However, there is also a possibility, and that occurred to Shane, that they are really clustered. And so our problem was to find out, are they clustered or are they not clustered? And if they are clustered, then what happened to these clusters, you see? So that was, again, the same mechanism, that somehow, you assume that somehow the cluster centers are distributed in space, somehow. On the field, we assume that the cluster centers, those egg masses, are distributed more or less uniformly. The agriculturists try to select uniform field with some particular plant grown on it, corn or wheat or whatever. So uniformity was a kind of a logical assumption to make. However, in space, who knows? So that was the subject. Also, if they are clusters, how big are they clusters? About how many elements, how many galaxies belong to clusters. Also, at the time, there was a very famous astronomer, Hubble. He shown that it looks like the universe is expanding. Now, all right, universe is expanding with some Hubble law. All right, now what happens to clusters? So suppose we have a cluster. It's expanding, meaning it participates in the expansion of the universe. That's to say, its center, call it, drifts away from us, from other galaxies. But what about members? Do they expand? Do they participate in the expansion or not? That was one of our people tried to find whether this is so or not. Then there was a paper, and well, I got an invitation to write one in French, to publish in France. There is a serial publication there of Institut Henri Poincaré, and so a big paper there also to assume that yes, there is clustering, but does this clustering support or does it not support the hypothesis that the universe is expanding? The Scott produced a paper which got labeled in the astronomical literature Scott effect. You have to try to estimate the distance of the cluster or group of stars from the observer, from us. And so she assumed that all you have to do is to measure the brightness of the most bright galaxy, you see. And it varies in a particular way and so forth. And then some astronomers started correlating there. Does the Scott effect exist or not? So this paper is also mentioned there. But the most exciting study there was about, when was it? Yes, it was in the 50s. Quite inspiring, really. There is an Armenian astronomer called Mr. Abartsumian in Soviet Union, in Soviet Armenia. And he started his investigations by studying stars. In Armenia, in Soviet Union, there are no big telescopes comparable, or they were not. Maybe at present they are, I don't know. But at the time, they didn't have it. And so this what happened. International cooperation to study the universe. The observations came from United States, usually from Mount Wilson. That's Mount Wilson near Pasadena. There are big telescopes there, observations. All right. And this included the sky survey. And they did something like Shane did, just photographs of the part of the sky which is visible from them. And these photographs, they are nice, but they are inexpensive, and so this was sold, and to have it in Stat Lab in Berkeley, a bunch of them, not all. All right, and then the astronomers in Moscow, and particularly one named Vorontsov Vilyaminov is difficult to pronounce a little bit, and so he is known in the United States as VV. So he examined all these photographs, all the full collection, and examined all right with magnifying glass and so on, and he published a catalog of peculiar galaxies. All right, this was done in Moscow, and then in Pasadena they bought this catalog. And then there is a very enterprising and quite inspiring gentleman, Dr. Arp, Halton Arp, I think his name is, and he those are peculiar galaxies. They are somehow out of the ordinary. So he used a big telescope to photograph them. And I tell you, these photographs are most inspiring. And then these photographs were sent back to Moscow and examined there. And that same VV described some of these photographs like by a term mouse tails. And that's a bunch of little galaxies, all right, on the photograph. And then they have jets. And these jets, just like mouse tail, you see, and some of them are connected, very interesting. All right. And then Mr. Ambartumian, I know I've been in this observatory. He has a radio observatory. It's just on the border of Soviet Union, and then a little further on there is a boundary, and on the other side there is a Mount Ararat, you know, all right. So, but no optical. And studying these stars, he conceived the idea that of a new kind of association of the star, and that's what he called not cluster, not star cluster. You can see star clusters during the night here and there, but they are not very near, but they are more or less of the same age. And this suggested to him, and they move apart, that those must be stars which were born more or less at the same time, and then they disperse. And presumably, why do this? Presumably, there was some force which kicked them out. Presumably, there is must have been an explosion. That was his original idea. And then he started looking at the galaxies and saying, yes, presumably galaxies also explode. All right. And so that was in Armenia, but here in the United States there is a very talented, interesting couple which are described, I hope no one would take offense, Beauty and the Beast, husband and wife. Yes, and Beauty is the leader, and Beauty produced observations of some galaxies which happen to be so located that that you see them face on. And so galaxy is something like this, roundish, and in the middle there is a nucleus, white. You can see on the photograph a big white thing in the center. Now, she, remember, studied spectroscopy, you see, of this. And then came to the conclusion, also probably with the husband and some others, that there must be in this center of the galaxy, must be an explosion which ejects luminous matter, but not strongly enough so that luminous matter flows back. That was their result. All right. Now, Year of Grace 1958. There is a big conference. I didn't attend this conference, but I heard about it and read about it in Belgium. Solvay conference, just like this Pfizer Foundation gives money for these conferences. So Solvay, also I believe it's chemical company, provides funds for studies of astronomy and cosmology. So here comes Mr. Barthumian and asserts that the galaxy must be exploding, and then the clusters of galaxies are formed, and that's what I see. Well, there was quite a bit of skepticism about it, but then already here in the United States again, there was a special conference, and people got, now with the help of Mr. Arp, you know, the one who has photographs of peculiar galaxies, it's accepted. Yes, galaxies must be exploding and clusters must be falling apart. I tell you, this was a very kind of exciting and very interesting period in my life when I was participating a little bit in it. All right. Now, clustering there is somewhat similar to clustering of larvae. Namely, it's just one cluster. Right? So, cluster of larvae, starting with the mass of eggs, larvae disperse. Yes, there is a galaxy. This galaxy, for some reason, I wish I knew, and other people don't quite know yet, I believe, explosion. A galaxy explodes and then ejects masses of luminous material, and these masses create new galaxies. Yeah? So just one explosion here and one mass of eggs here. Yes, the dispersal of these galaxies from the center, well, they must be of different kind of dispersal of larvae. How far do they go? Who knows? Larvae are limited, those are not. And there are various difficulties. Larvae you can count in a given square, but count galaxies, you cannot go there, too far. So there are difficulties, there are differences, phenomenally the same, but you study it somewhat differently. All right, now third field of study, again, galaxies. If I may have the permission of the ladies, I will light a cigarette. I am a little allergic to absence of the cigarette. All right. So, I happen to be in Europe. And, yes, many people did at the time, brought a car with me. Okay? Now it appeared that in order for a car to be brought, to be admitted to the United States, you had to have a certificate that it was properly washed. Why? Because it was found that before this regulation came out, you had to, the cars brought from Europe brought seeds of weeds which were not known in the United States. And so, in some localities on the East Coast, would start a development of epidemic, if you like, of some kind of weed which didn't exist before. And so, there were several firms in Europe which had the authority. You have to pay him for them to wash the car, wash away the wheels, the tires, and then they give you certificate. Then you bring this car to United States, show certificate, then you are admitted. But if it isn't, then the car is but they don't throw it away, I presume, into the ocean, but there are some difficulties. So that's how the idea came. Now, so there is a development, clustering, but somewhat different from larvae. So there is a seedling brought from Europe, and it was not eaten by birds and anything, and it produced a plant. Now this plant, the plants are self-fertilizing and not self-fertilizing. But if it is self-fertilizing, then the plant grows, produces a number of flowers. They are self-fertilized. The seeds are forming, became ripe, and then when they are ripe, the wind comes and carries them. So what is here? This original place where the seed started growing, it's a cluster center. Then there is a number of cluster members, and they disperse, somewhat like larvae, isn't it? And also presumably they don't disperse too far, so there must be an area of accessibility. But what is the difference? The difference for larvae is just one process of clustering, and then it stops. However, for these weeds, you have one weed, one seed produced a cluster this year. Next, then they will disperse. Some of them will be, the seeds will be eaten by birds, all right. So it will be varying number of cluster members, and each of these cluster members that survives up to next season is a source of a new cluster. So there is a succession of clustering, and that's what, if you look, how would you discuss it? How would you describe it? Well, that's population dynamics. It's a problem of population dynamics. It starts with a few original seeds, 1, 2, I don't know how many, and then next year there is a progeny. Year after there is a progeny. Yes, it's possible that every one of them would be killed, could be eaten and so forth, subject to chance, but the essential point of clustering is there, only is succession. All right. And then what happened in the United States, this is another domain, more complicated in one way because there are generations, one after another, the population dynamics. And then, now quite a few of us here would remember that there was a huge epidemic of polio, at which time something like 50,000 kids, mostly in the south, became infected during a particular summer. And after that, this phenomenon attracted the attention, just like cancer attracts the attention of people now. And so people became interested in the mathematical theory of epidemics. Well, all right, and so I was also I became interested, and then I remember the book by now what was the name of the gentleman? Well, it came out. It is here somewhere. Who wrote a book on the theory of epidemics, And it appeared that the first study of epidemics was due to a British civil servant who served in I believe in India. He had a daughter, but being an English civil servant of some standing, he decided that he should send his daughter to a boarding school in London. And it appeared that while the girl was there was an epidemic of a flu, I think, and all the girls were sick in this boarding school.
Excuse me, Dr. Neyman, we must pause for a moment to change cassettes.
All right. What?
Go.
All right. The basic assumption of this very old-fashioned theory was that a single infectious increases the probability in the same way of all susceptibles which are available in the population that you study. Now, all right. So in the boarding school, in the dormitory, this may be true. But if you take the epidemic which develops in a city or in a country, all right. So someone becomes infectious in New York. Does it affect very much our chance of being infected? No. You may infect some people and they could disperse and then infect us. That's a possibility. But that same individual, the first, but that's wrong. So we constructed a theory of epidemic, which then appeared to be realistic, which contains the following elements. Yes, there is a single individual who is infectious for a very brief period of time. He infects a number of susceptibles around. Then these susceptibles disperse. And if he infects these people, let's say by sneezing, in the bus, then he infects many, and the bus distributes them all over the scene. However, if he is fishing, like there is a book, 3 people and a dog in the boat. Well, he cannot infect many. So the number of infected depends on the place where the infectiousness occurs. That was the basic thing. And then there is a dispersal of these infected. After a certain period, they become infectious and so forth. There is a continuation. There is a cluster of clustering of clustering of clustering. So that was our theory. Then I was teaching it, and in 78, a lady came to the course, Mrs. Morrison. She is an employee in California State Health Department, and she listened to it and said it's all wrong. She was delicate, she didn't say in these words, but it was convincing. And then, what is wrong? The number of people infected by a single infectious does depend on the locality where this infectiousness occurs, all right, but it also depends on the place where the infectious usually lives. We have in the Bay Area slums, and these slums, many people around, and if one of the inhabitants of the slums becomes infectious, he or she will infect many people around him. They live there, close contact and so forth. However, if a rich man who owns a chain of some stores located in the slums, if he comes to the same place, he will infect many fewer because he will have contacts only with managers of these local stores and so forth. And so, in order to construct a realistic theory of epidemics, you have to make it more complex. The number of infected in a particular place does not depend only on the particular place, but also on the personality or where does the infectious individual live. And so this inspired, and we had a very interesting period. People tried to use simulation to produce how these epidemics develop. And in our theory, the old one, there were two theorems which I like to call democratic theorems. They show this, that if there is a locality very nicely hygienic conditions and so forth, but there is a probability, not zero probability, that people from other places can come there, then there is high probability that the efforts of having this particular locality, hygienic, to prevent the explosion of the big epidemic, these efforts will be probably not successful. So that two theorems, they prove that. And then we wanted what we did by simulation, something similar, more complicated, and we had a rather international group studying it. One individual was Professor Odum from Ghana in Africa. I didn't know where Ghana is. Another from Venezuela, and we hope to have this summer, during the summer, prepare a paper on epidemics, something joint. So this is going on, and I am rather interested in possibility of mathematical theory. Mathematical theory we are not ready. All right, but now let me tell you something about the clustering in another domain, and this is radiation carcinogenesis. There are published many theories of radiation carcinogenesis, but we thought, and we means, in addition to myself, Professor Prem S. Puri, now at Purdue, yes, my former student, very active, and so he spent his sabbatical in Berkeley, and then we came to the conclusion that the existing theories of radiation carcinogenesis, that they are not realistic, and he, I must say, was accumulated tremendous amount of factual information. And so we wanted a realistic theory of this, and there clustering comes. Well, first of all, there are, I don't know whether I am now showing this. Oh yes, that's the title page of our article, this Puri. And then the subsequent slides show the phenomenon which you would like to, which you want to, no, not this one, oh yes, this one, which I'd like to illustrate. So what happens is that here is the phenomenon of dose rate effect. On the horizontal line you see dose of radiation, and just let's see 300 rads. So mice were subjected to radiation of 300 rads by gamma rays. And there are three curves. Now, the difference between three curves, essentially there are two very similar, but that was low rate of application of this dose. So the mice were exposed to this radiation over a long period of time, and then, all right, the total dose that they received, well, let's concentrate on point 300 rads. But then there is a top curve there. The same dose, but the same dose of radiation was administered in a very brief period of time. There is a figure there which shows how much of it, but it's a very brief period of time. So the dose rate was high. Now similar effect is another empirical finding, and that's empirical finding. Both of them are coming from studies of a gentleman called Upton. At the time he was just an employee with his MD at the Oak Ridge National Laboratory. However, there is some evolution, and at present he is the director of National Cancer Institute, and we may hope that when he is director, something effective will be done about cancer. So there are two kinds of these curves. Some are with the symbols, on the corners, are not filled. They are just, I don't know, rectangles or something of that sort. And if you look at them, it's gamma ray. You will see that there is a tendency going up and then going down. The again lower curve is small dose rate, and the other one is high dose rate, the upper ones. But there are also curves there which are filled, quite black spots. Now if you look to them more closely, you will see that there are several curves so close together that it's difficult to distinguish them. But I believe there are three of them. They're marked with black spots. It's a tremendous difference in dose rate, but you don't see the effect. This is radiation not by gamma rays, but by neutrons, different kind of radiation. So the people who work on it, biologists, whatever, they have a special term for distinguishing between these two kinds of radiation, namely LET, for brevity LET. It stands for linear energy transfer. So linear energy transfer of gamma rays is low, but for neutron is high. And you have high linear energy transfer with neutrons, and then dose rate somehow doesn't work. Why? So that's what attracted attention of Puri and myself, and we worked on it, and suddenly we got the illusion that we understand. Whether it is understood or not, we don't know yet, but we have the illusion at least, and the pleasure. And now let's see what we have to learn something about physics in order to understand it, energy transfer. And we also will know, we are discussing in a minute, that's a fact, that a photograph of a cloud chamber. And on this cloud chamber, you will see the photographs. It's a very remarkable thing, I must say. So, cloud, chamber, box. It's so arranged that that there are some walls of this box which are safely immovable, and they are difficult to penetrate. They are made of lead or something, and so they are protected. Radiation doesn't reach there. But one side is open, and so when the particle comes there, well, then suddenly the whole box expands. It's filled with this gas, and this gas becomes ionized by this radiation, and these ions become visible, and so the box is expanded, and immediately a photograph is taken, and you see what happens. Now, what happens is that there are traces of paths by particles which crossed the box, and some of these particles are rather fat, thick, across. There is a substantial area there. But some others, if you look more closely, the paths are very thin. And all right, it's a very good reproduction, but I tell you, if you look at in an actual photograph, there are very, very thin traces. So those would be different particles which create very little ionization, you see. But in order to obtain the strip white, you have to have what? Particles. The original particle passes, and it must create many, many, many other particles which, all right, they disperse, obviously clustering. They disperse, but they disperse so that tremendous area is covered by this. Now, all right, this is physics. And I must tell you another detail, which is not on the photograph, but the physicists told us that this occurs, all this, in a very brief period of time, namely 1 second divided by 10 to the power 12. It occurs substantially shorter than this, you see. So it's instantaneous. All right, that's physics. But this particular slide there, it illustrates not physical information, not information from physics, but musings of a biologist. And there should be two parts of it, panel A and panel B. Panel A, he described, this gentleman, that this is a low lead irradiation by gamma or X-rays, and you will see that there are many thin lines there. It's not observation, it's visualization, and there are several spots where the path of the particle is accompanied by accumulation of these secondary particles which do the heating. However, on the right, that's a path, as we visualized it, of a heavy particle, alpha particle, that would be high LET, and very just filled with concentrations of these particles, ions, as he's musing. So we had to combine this into the theory, explaining the difference between low LET and high LET, gamma and X-rays is low LET, and there are certain things which you can measure. So there are mice here, and there is a source of irradiation. Between mice and irradiation there may be a screen which would count the particles which are going into this direction, capable to hit a mouse. Those will be called primary particles. Now, if a primary particle hits a mouse, some particular tissue of the mouse, then what? It creates a cluster of secondaries. These secondaries may be few, if it is a gamma or X-rays, or it may be many, if it is alpha particles or neutrons. So this is what we manufactured 2 years ago, and this year we have the intention at least to spend a good part of the summer to develop theory in details so we could estimate the sizes of these clusters, area of accessibility, whatever. So this is the plan for the summer. And now I think I exhausted my material. Thank you very much for your attention. I enjoyed talking about it.
Our first respondent today is Dr. Frank Anscombe of Yale University. Professor Anscombe is widely known as an expert in statistical inference, and his papers on residual analysis are widely quoted in the literature. It gives me a great deal of pleasure to introduce you, Professor Frank Anscombe.
Thank you, Dr. Poston. It's a very great pleasure to be here on this very special occasion and to be invited to participate. Professor Neyman has traced the development in his research of a theme, the idea of a stochastic theory of uneven or clustered spatial distribution of something. He has pointed out that it is interesting to view the evolution of a simple and fruitful idea. The evolution is not apparent if we view only the contemporary state of the evolving idea. I have felt for a long time that some study of the history of statistical ideas is not only fun, but helps one to have a more vivid and accurate understanding of those ideas as they are now. When we read a concise, elegant, and comprehensive treatment of a topic in a recent book or review article, it's all too easy not fully to appreciate how much is represented by the brief statement and how particular instances of the topic will appear. For example, we are all familiar with the chi-squared test of goodness of fit of a set of counts to a supposed multinomial distribution, or of the entries in a contingency table to a hypothesis of no association between the row categories and the column categories. The topic is presented in most elementary books on statistical procedures or statistical theory, and it seems mostly pretty simple. Many of us are aware that there has been a very large literature exploring various particular or special questions related to the chi-squared test, or exploring lines of thought that take the chi-squared test as a starting point, or that replace it by something else. Some of that literature is not so simple. And parenthetically, I may add, it will surprise no one if I say that Professor Neyman has made distinguished contributions to this literature. For a basic understanding of the ordinary chi-squared test, it seems to me that there is no good substitute for actually reading Carl Pearson's original paper of 1900. It's one of the great papers in our subject. From a modern point of view, it can be criticized. Pearson makes heavier weather than necessary of the mathematical derivations, and he does not quite correctly understand the business about degrees of freedom. Yet he had then, in 1900, the great advantage over us now that he was investigating a new question, for which there was no generally received answer, and with which there was no reason yet to be bored. We see that he did what he did with some struggle, and that he had some sharp perceptions of what he was trying to do. If one assimilates the portions of his paper that are still persuasive, and if one thinks about the features that now seem capable of improvement, one has altogether a firmer grasp of the subject. I should like to mention one further example, and this concerns a much bigger topic, namely sampling methods. Since the end of the Second World War, there has appeared a large literature of books and of course papers on sampling methods concerned with the procedures used by the Bureau of the Census, the current population survey, the organizations for opinion polling, and other governmental and private agencies. Many of the methods used are very ingenious, rather complicated, and not easy to understand fully. It's a subject where the reader may easily be overwhelmed by details. Some very basic matters are typically mentioned rather briefly and somewhat taken for granted. Some of these basic things come into focus only when we look at literature dating from before the late 1940s. In the early years of this century, there was much discussion, some of it under the auspices of the International Statistical Institute, about the nature of representative samples. Should they be obtained through random selection, or should they be chosen deliberately to reflect the population with little or no reliance on blind chance? The early literature is remarkably confused. Then, in 1934, came the famous paper by Professor Neyman entitled "On the Two Different Aspects of the Representative Method." Here, for the first time, an expert mathematician brought light to bear on the murky topic of sampling. General principles were stated clearly and precisely, and illustrated by simple examples. Suddenly, there was a firm, clear base to build on. It should not now be overlooked. That also is one of the great papers in our subject. I'm sure that all of us here today have greatly enjoyed Professor Neyman's fascinating reminiscences. His researches in clustering have been going strong for 40 years, taking many unexpected turns. he and others will surely continue to develop these ideas for a long time to come.
Thank you, Dr. Anscombe. Our second respondent is Dr. David Salzberg, Senior Statistician, Central Research Division of the Pfizer Corporation. Dr. Salzberg is an expert in design and analysis of biometrical experiments and has extensive experience in data analysis. I am pleased to introduce to you Dr. David Salzberg.
Thank you. Thank you. I appreciate this opportunity. In a way, statistics is a form of applied math. And as a form of mathematics, once in a while you run across some very beautiful mathematics in it. As I've gone through Professor Neyman's papers from time to time, although he often has many collaborators, I've been very pleased by the beauty of the mathematics, by the clarity of vision I frequently see. About 8 years ago, I had an opportunity for the first time to read through this 1939 paper that laid the foundations of what we've heard about today, the development of contagious distributions. And as I read through it, I discovered probably one of the great mathematical gems of papers that I have read. In particular, Professor Neyman developed the idea of these larvae moving out into a field. He introduced a general descriptor of the probability distribution of where they would be within the region, keeping it in a very general form, a G parentheses XY sort of thing. And as I read along, I said to myself, aha, now he's caught himself. He's out here in the middle of this field with this extremely important function completely undefined right in the middle of his picture. He can't possibly go any further. When at that point he introduced, in place of this G function, the average across the entire region and developed a one-parameter distribution. Backed up, broke the region into two pieces and introduced the averages on each half and developed a two-parameter distribution and so on. And I looked at that and I suddenly realized what he had done. He had taken that old proof of the distribution of conditional probabilities, and he had recreated it in a new gown, in a new place. It was like listening to the last movement of the Franck Symphony and recognizing a fragment of a melody from the first movement completely appropriate in its proper place. Professor Neyman, as one of the younger practitioners of the field, I was only 8 years old when that paper came out, I want to thank you for introducing some beautiful and very nice mathematics into the reading that I've done. But statistics is more than just pretty mathematics. In fact, there's very little pretty mathematics in statistics, because statistics is the business of applying some fairly complicated ideas to some extremely complex kinds of data that exist. About 1893, when Carl Pearson first introduced the ideas of skewed distribution, we have a very original and possibly different kind of philosophical view that had never existed before. Carl Pearson suggested that it was possible to take something which people would dismiss as pure randomness, as uninterpretable noise of some sort in the biological field, and fit the patterns of randomness to classes of distributions, and thereby learn something about them. Well, Pearson's approach was to create a fairly dense class of distributions, somewhat like the polynomials to which we fit continuous variables. But he was to create a fairly dense class of distributions and attempt to fit the data as it fell within that class of distributions. In this 1939 paper, Professor Neyman raises a very interesting point. He states that there are two ways of developing the distributions, the probability distributions that would describe the material you have at hand. One is to go about it Pearson's way, finding some sort of large class and fitting within that class. That's pretty much the sort of thing we do with multiple linear regression now. The other was to start from the basics, try to construct a family of distributions based upon what we know about the underlying characteristics of the procedure. We never may be able to measure the nature of the underlying characteristics, but by looking at the classes of distributions that come out, we can make some inferences about these underlying characteristics. What he ended up doing was counting the number of larvae in a small region in a field. He had no idea of how many egg masses had been laid, or how many of the how large each mass was, or what the rate was at which these larvae were going to be killed off. But by introducing a set of parameters into his distribution, he was able to create a situation where you could try to fit the data to this particular class of distributions that you have. Now, what's the advantage of that? Well, Professor Neyman, again, in some of his work on the restricted chi-square test, has pointed out the main advantage. If the class of distributions into which you're going to fit your data describe all the reasonable alternatives, then you have a tremendous amount of power in being able to distinguish between various underlying events that might have given rise to it. And this is why I'm particularly interested in his more recent work on radiation carcinogenesis. I've been doing some work on chemical carcinogenesis, so I can recognize the difficulties of the problem that lie here. What we have, to put it on a very social kind of basis, is a great amount of fear as to what the nature of uncontrolled or uncontrollable radiation might have upon the future health of the communities in which it occurs. We have a recent scare of a atomic energy plant which released something like 1,200 millirems of radiation, and somebody predicted there would be 40,000 cancers as a result of that particular release. Well, these predictions are based upon a very conservative model called a one-hit model, which is a kind of, it assumes that there's a Poisson distribution to the events that are going to occur, and that whenever one event occurs, it leads irrevocably to cancer. It's the most conservative model you can create. But if we're talking about public health, sometimes we're forced to deal with the most conservative model. If all we had to do was prevent the items, the events leading to it, there'd be no problem in dealing with the most conservative model. But unfortunately, we're faced with a trade-off. We have to decide how much radiation should be allowable, since some of it must occur as a result of the ordinary experiences of life. And so now we're stuck. We can't use the most conservative possible model, but we've got to somehow work within a class of models that is sufficiently small so that we can get ourselves decent bounds, decent probability bounds on the parameters of those models. And this is where Professor Neyman's more recent work is very exciting to me. Because what he's done is he's expanded beyond that single cluster of larvae out in the field, and he's noted that there are 3 clusters that result in the cells that have been hit by the irradiation. One is a set of cells which are going to be so badly damaged as to die and have no progeny. Another is a set of cells in which an inheritable change is going to occur in the DNA and lead eventually to some sort of a cluster of daughter cells which are, if not cancerous, are protocancerous. And the third are the set of cells which are repaired by some repair process. Well, we can see this repair process in operation. For instance, in chemical mutagenesis, the most potent mutagens that you have are not carcinogens. That is, those chemicals which at the smallest amounts appear to cause the greatest amount of mutation in living cells do not appear to cause cancer in living animals. And one reason why that is, if you actually look at the something called unscheduled DNA repair models that they have, if you look at the rate at which the cells are capable of repairing the damage done to their DNA, there's a fundamental element in a cell which enables it to do this sort of thing, against the rate at which the cells die out. Recognize those are 2 of Professor Neyman's 3 clusters. If you plot those for very potent mutagens, what you usually find is that the rate of cells dying off increases so rapidly that before the repair mechanism has been saturated, almost all the cells have died off. And so what you have in that situation is a modification or a set of parameters of the distribution whereby only 2 of the clusters have much probability of remaining, and the third cluster, which we're most worried about, has a very low probability of coming about. What Professor Neyman's model has done is it's provided us with a very small but very well-defined class of distributions. And I wish him a great deal of luck and future development along here, because I think within that class we may be able to get ourselves a reasonably conservative model that will enable us to predict the carcinogenicity from radiation and still not be worried about doing something in a blind and least profitable fashion. So, Professor Neyman, as a younger practitioner, I want to thank you for the beauty and pleasure you've given me, for the insights you've given me, and I hope that we can all appreciate a great deal, or we can all gain a great deal more from these clusters that you've already started.
Thank you, Dr. Salzberg. Our final respondent is Dr. Gottfried Noether of the University of Connecticut. Professor Noether is an internationally recognized expert in the field of nonparametric statistics, and he has published extensively in this area. He has in particular a strong interest in the area of confidence intervals, an area developed by Professor Neyman. I'm pleased to introduce to you Dr. Noether.
Thank you, Dr. Austin. Professor Neyman has presented a stimulating Pfizer colloquium in which he set out to illustrate the phenomenon of the evolution of an idea. Throughout his scientific life, Professor Neyman has been involved with the evolution of probabilistic and statistical ideas in the study of nature. Today's talk, together with two other recent papers, namely a glance at some of my personal experiences in the process of research and frequentist probability and frequentist statistics, provide fascinating insights into Professor Neyman's way of thinking and his many-faceted contributions to statistics. To somebody like myself, who over 30 years ago had the good fortune of having had Professor Neyman as his teacher, these three papers have a particular appeal. It so happened that Professor Neyman, along with a copy of his present manuscript, sent me a reprint of the frequentist paper, which I've just mentioned, and as a result it occurred to me that I might use this occasion to relate an occurrence in the early history of confidence intervals, which I have not seen mentioned before, and of which even Professor Neyman may not be fully aware. But let me first provide some historical background for those students in the audience who will be familiar with the general theory of confidence interval, but not with its history. Until the 1920s, a principal tool of statistical estimation was Bayes' theorem, with its requirement of a prior distribution for the parameter to be estimated. Both Fisher and Neyman, as well as other statisticians, recognized the difficulties inherent in postulating such a prior. To get around the difficulty, Fisher introduced what he called the fiducial argument, an argument whose relevance, to use the words of Henry Sheffey, is either not understood or accepted by many statisticians. Fisher then used the fiducial argument to derive what he called the fiducial interval for the parameter to be estimated. At about the same time, Neyman attacked the problem of interval estimation from a semi-Bayesian viewpoint. Even though he started from an assumed prior, he insisted that the resulting interval estimate should have frequency properties that were independent of the assumed prior. A later suggestion by one of Neyman's students, Churchill Eisenhardt, led to the now generally accepted formulation of a confidence interval as a random interval which covered the fixed but unknown parameter value with a prescribed probability. At first it appeared as if Fisher's fiducial intervals and Neyman's confidence intervals would in practice produce identical results. And Neyman was prepared to concede Fisher's priority, insisting only that Fisher's interpretation was faulty. But Fisher roundly dismissed such a possibility. In time, an example was found involving what is now known as the Behrens-Fisher problem, where it became quite evident that the two approaches to interval estimation cannot be reconciled. The solution which was advocated by Fisher, and which was based on some earlier work by Behrens, did not permit the frequency interpretation which is so essential to confidence intervals. I have been interested in Behrens' work in nonparametrics, and from time to time I have wondered what Behrens' reactions might have been over the Neyman-Fisher controversy concerning the so-called Behrens-Fisher problem. This is what Fisher wrote in 1939. The solution of this problem has been known for nearly 10 years. Behrens proposed and gave the correct solution to a perfectly definite problem. End of quote. I'm not aware that Behrens ever took issue with this statement, but then it was made just at the beginning of World War II, and Behrens had his own problems in Nazi Germany. But it seems to me that there is considerable evidence that Behrens could not have agreed with Fisher's interpretation. As I read Behrens's 1929 paper, I have a feeling that Behrens' outlook on statistics is much closer to that of Professor Neyman than to that of Fisher. Again and again, Behrens reminds the reader that probability statements are to be understood as long-run frequencies, im Durchschnitt von unendlich viel Fällen, as he puts it. This is not what Fisher seemed to have in mind when it introduced fiducial probability. Behrens apparently developed doubts about the general validity of the approach advocated in his 1929 paper rather soon after its appearance. In 1933, in a very little-known book, Mathematische Methoden für Versuchsansteller, Mathematical Methods for Experimenters, Behrens formulates what is now known as the Behrens-Fisher problem and then states, "To the best of my knowledge, this problem has not been treated before." This is 1933. A short footnote refers to his own 1929 solution, disposing of it with the words, "In an earlier treatment of this problem, it was tacitly assumed that the population means were uniformly distributed." The reader is left to draw his own conclusions. To anybody familiar with the German statistical literature of the 1920s and 1930s, Behrens' book is quite remarkable. I've written about some non-parametric aspects elsewhere, but the following quote is relevant to the present account. After discussing the one-sample t-test, Behrens computes an interval for the population mean and then adds, "The assertion that the population mean lies between 29.4 and 36.4 belongs to a class of assertions which are correct 98% of the time and false 2% of the time. I wish that present-day statistics text contained as unambiguous language as Behrens' book did nearly 50 years ago." Thank you.
Thank you, Dr. Noether. At this point, I will invite Professor Neyman to provide us with any of his final remarks.
Thank you. All right, so I did have a dispute with R.A. Fisher, long time, and it ended, I believe, in 1961, when there was a meeting of International Statistical Institute in Japan, in Tokyo. And at that time, a number of us who attended were invited by Japanese organizations for some lectures and so forth. So Fisher was invited by a society, I forgot the exact name of society. Well, and he went there and he spoke, and then they published his paper, and then I received from the society a letter saying that herewith is the issue where Professor Fisher, Sir Ronald Fisher, contributed an article, and my name is frequently mentioned. And if I wish, I could have a similar space in the journal for response. So I read it and wrote a response which has the title, Silver Jubilee of My Dispute with Fisher. It was published, and that was my last contribution to the dispute. However, soon after that, Fisher died. Fisher died, and then I thought it appropriate for me to write another paper about Fisher, and the paper appeared in Science. R.A. Fisher and appreciation. My point is that yes, we had dispute this and that. I still continue to believe that on some points Fisher was wrong, but at the same time I rather think that the Fisher is one of the creator of modern statistical theory, and tried to describe what he actually did. Everyone makes mistakes or is impolite occasionally or something of that sort, but an individual, when he is already out, and then he should be judged not by mistakes but by his achievements. And I consider the achievements of Harry Fisher tremendous. Many concepts which he introduced, concept of sufficiency, concept of efficiency, concept, a number of them, they are still in the books. And if you look at the present literature, there are the efficiency, this is efficient, this is not efficient, slightly different possibly definition of it. It's still being discussed. But the greatest achievement of Fisher, from my point of view, and that's subjective, is his construction, his initiation of the problem of design of experiments. This is something which really is tremendous, and there are many problems of design of experiments now. Yes, different fields, but the problem of how to do it. And so I think it's appropriate for me to state that apart from various personalities and so forth, my respect for the work of Fisher is tremendous. Well, that's probably is summary of my reactions to what I heard. All right. The one thing, perhaps, that there are ideas. You see, each of us owns something. Yes, I own an automobile. However, this ownership of automobile or a house, that's one thing. But idea, if someone creates it, see, this is an asset which must be recognized. The one who would try to steal someone else's idea, well, it's worse than the stealing, let us say, of the automobile or something of that sort. And here I must say that many ideas which I developed, work on them and so forth, stem from my students. And one of them was mentioned, these confidence intervals, that I started these confidence intervals as a quasi-Bayesian, as described in the article which was mentioned here. And then my student at the time, Churchill Eisenhower, that was in London, and he attended my courses, and then on occasion there would be a tea party in that same department every afternoon, of course, in the department, but then we had a walking party and so forth, and so he once told me, Mr. Neyman, it would be so nice if the theory of confidence intervals would look nicer if it were entirely free from Bayesianism. And that inspired. And so, some years later, I produced a theory which is independent. All right. Then there is another man who was mentioned in the paper, 3 minutes. And that's Herb Robin. I tell you, he produced a theory. He essentially solved the theory, solved the problem which occupied mathematical statisticians for centuries. And under the name it's known as the empirical based methodology. And to my regret, in our department, people hear that such exists. But there is no courses, no book in which you could read this stuff, application and so forth. I saw Herb recently, last week, in North Carolina, and then tried to rub into him the idea that he should find someone who would help him to write maybe 150 pages or so of a book from which it could be learned. The point is that there are people who are writing books, many, and there are people who do research, but somehow the spirit of this research prevents them to write book, and then the very brilliant idea begins to be lost. Thank you very much. I enjoyed the meeting tremendously.